All right, so our next reaction type are another type of substitution reaction. So we've seen one example of a substitution reaction involving alkanes, that being a free radical substitution reaction. This one is significantly different. We're talking about substitution reactions involving halogenoalkanes. So halogenoalkane contain an alkyl group, so basically carbon containing branch or carbon chain bonded to some halogen, chlorine, bromine, fluorine, or iodine. So example, um, chloroethane or chloromethane is a halogenoalkane. And so we're talking about just a mono halogenoalkane. So these reactions occur via different mechanisms. We'll see this in a bit depending on the type of halogenoalkane. But this much is true. The rate of the reaction is faster, and I don't really like to use that term. The rate of the reaction is higher. The reaction is faster when the bond with the halogen to the alkane is weaker. So the more easily that bond can break, the faster the reaction. Therefore, reaction rate decreases when the attached halogen is smaller, or the rate increases when the attached halogen is bigger. So the bigger the bonded atom, the weaker the bond, and the more easily that bond breaks, the faster the reaction. So again, these are known as, this type of reaction involving a halogenoalkane are known as nucleophilic substitution reactions. So we have, again, free radical substitution versus nucleophilic substitution reactions. And so just like we talked about in the previous lesson, an electrophilic addition, an electrophile is a substance that loves electrons, a substance that has a region of partial positive charge that makes it susceptible to attack from a pair of electrons. This is kind of the opposite. A nucleophile is something that loves a positive charge, positive loving. Sometimes abbreviated just generically Nu with, we got, see there, a lone pair of electrons. So nucleophiles are negative ions or molecules that contain a lone pair of electrons, and the nucleophile is trading places, if you will, substituting for the halogen. So the halogen in the halogenoalkane is always what is being replaced by the nucleophile. Nucleophiles include water, this NH2 ion, ammonia, Cn minus or cyanide ion, or hydroxide ions. The rates of the reaction is faster also when the nucleophile is a better electron donor. Remember that an electron pair donor is a Lewis base. So the better the Lewis base, the faster the reaction of this type. As just mentioned, these reactions occur via different mechanisms depending on the type of halogenoalkane. We'll see that reactions involving tertiary halogenoalkanes, we'll review what that means in a bit, are the fastest due to the formation of a more stable intermediate, that being a carbocation, while those with primary halogenoalkanes are slower due to the formation of this highly unstable transition state complex that forms. So I already mentioned this. Different mechanisms. All of these reactions occur by heterolytic fission. So where when the bond breaks, the 2 electrons of that bond go to 1 atom versus what we saw in free radical substitution, where you have the homolytic fission of the bond between the halogen atoms. That is not the case here. All right, so let's take a look at a substitution reaction involving a primary halogenoalkane. And let's say we have something like, I don't know, chloroethane. Sorry, yeah, we'll do chloroethane. So I'm going to write it this way. I do also like to do, like your textbook does, and show these structural formulas with our 3-dimensional models with our solid and dash wedge. And so we can kind of see what's happening with this reaction. So again, it could be just chloromethane, chloroethane, chloropropane, but it's got to be some sort of halogenoalkane, and it's got to be primary. So remember that a primary halogenoalkane, the chlorine that the carbon that the chlorine is bonded to, in this case, is bonded to two hydrogens. I don't really like that explanation though. Better for me to understand why it's called primary. Because if it's two hydrogens, like two, okay, that maybe means like secondary. Why is it called primary? Well, the carbon that the chlorine is bonded to one other chlorine atom. And so because of that, that makes it a primary halogenoalkane. So reactions involving primary halogenoalkanes, what we see is that the rate law for these reactions indicates that both the halogenoalkane and the nucleophile are first order for each, which indicates that both the halogenoalkane and the nucleophile are involved in the rate determining step. Remember, the rate law comes from the rate determining step. And in this type of reaction, both the halogenoalkane and nucleophile are involved in the rate determining step, and therefore this is a second order overall reaction, or we refer to these reactions as bimolecular. We'll see it on the next slide, and it's a little bit further down in your notes, but I want to introduce the term now. These reactions occur via what is known as an Sn2 mechanism. Sn2, here, I'll just go to the next slide so you can see what that says. Sn2, which stands for substitution nucleophilic bimolecular, where once again, very, very important, both the halogenoalkane and the nucleophile are involved in the rate determining step. This actually occurs via a one-step mechanism, so be careful with this 2 here. This 2 does not mean a two-step mechanism. This means bimolecular. So you have both substances, both reactants involved in the rate determining step, and this is basically a one-step mechanism. This mechanism involves the formation of a transition states complex. So let me draw out my nucleophile and the chloroethane and show you what's going on here. All right, I think I'll start with drawing two-dimensionally, and then later on I'll show you with our other models that are more 3D. So I have my halogenoalkane, I have my nucleophile, and so we'll talk about in a bit, but these hydrogens are very small, and so this means that this carbon atom here is wide open to attack by the nucleophile. Now, why is this carbon attracted to the nucleophile, or why is the nucleophile rather attracted to this carbon? Well, this bond here between carbon and chlorine is rather polar. Halogens are some of the most electronegative elements, and so that makes this a very polar bond, which makes the carbon end of that bond partially positive, which makes it susceptible to attack from something that is negatively charged or has this lone pair of electrons. And so let's get rid of that. Oops. And so once again, we want to use our curly arrow to show. We always start with the source of the electrons and show where those electrons are going. So again, this nucleophile could be a hydroxide ion, where that pair of electrons is used to make a bond. In this case, it's going to be between oxygen and carbon. It could be an ammonia molecule or that NH2 ion. Again, we have a lone pair of electrons. This time we would form a bond between carbon and nitrogen. So wherever the lone pair of electrons are, those electrons will be used to make a bond with the carbon. So let me erase this and we'll continue with the mechanism. All right, so here's what happens. So again, both of these are involved, both substances are involved in this rate determining step. And so what we end up with is a transition states complex that forms. where both the nucleophile and the halogen are bonded to carbon. We have actually carbon forms kind of like 5 bonds, even though we have the simultaneous formation of a new bond and breaking of an old bond. Let me draw that out and show you what that looks like. All right, before we look at this transition state complex, let me back up a little bit. So we have these 2 electrons here that are being used to form a bond with carbon. Simultaneously, we have the electrons in that bond between carbon and the halogen going to just the halogen. So we have, again, simultaneous formation of a new bond and breaking of an old bond. And so we kind of show that with these dashed lines here. So anytime we have a transition and intermediate particle here, especially in this situation where we have a negative charge, and so we want to put that transition state complex in brackets with the charge. And so we have these dashed lines showing that this bond is forming at the same time that this bond is breaking. And then this, I don't want to say last step, because this is all kind of happens simultaneously in one step. We have the completion of the formation of the new bond and the completion of the breaking of the old bond. And then we end up with our product. Whoops. And again, I'll just draw this with the 2-dimensionally tetrahedral arrangement. And that is our product along with, that's our organic product. And we are losing that, so we end up making Cl minus. So that's, whoops, that kind of looks weird. So you make the organic product, which is here, and then our inorganic product, which is Cl minus. So let's do this. Let's go through this, even though you can rewind and rewatch. I'm going to go through this one more time. So we have a primary halogenoalkane. So the carbon that the halogen is bonded to just one other carbon atom, which makes it primary. This bond between carbon and chlorine is polar, and as a result, the carbon end of the bond is partially positive, which makes it attractive to a nucleophile, or something that has a negative charge or has a lone pair of electrons. And so this lone pair of electrons on the nucleophile is used to make a bond with carbon. While this bond is forming between the nucleophile and carbon, this bond between carbon and the halogen is breaking. And we have, for a very brief moment in time, both the nucleophile and the halogen bonded to carbon in this transition state complex. Remember, transition state complex is this intermediate particle. It's made of the reactants, which are on their way to forming the products. So when these reactants collide, momentarily everything sticks together and you make this intermediate. This bond forms completely. This bond then finishes breaking and you end up with your product, organic product. And then, of course, in this case, we are producing chloride as well. So this is bimolecular, and this occurs via a one-step mechanism. All right, so what if you have a tertiary halogenoalkane? So the reaction essentially is the same. We have a substitution reaction, but how this reaction occurs is very, very, very different than what we just saw. So once again, a tertiary halogenoalkane has the halogen, the carbon that the halogen is bonded to 3 other carbon atoms. So let me show you an example of that. Sorry, got to squeeze that in there. So what is this called? This is called 2-chloro-2-methylpropane. Now, sometimes I said the number is not necessary, that methyl can only go on number 2, but the most common name for this is 2-chloro-2-methylpropane. This is a tertiary halogenoalkane. So let's look. The carbon that the chlorine is bonded to 3 other carbons, or no hydrogens. This is tertiary. All right, so rate law for these reactions indicate that only the halogenoalkane is first order, which indicates that only the halogenoalkane is involved in the rate determining step. So you have one substance involved in the rate determining step. And so as a result, this type of mechanism or reaction is referred to as unimolecular. So that has implications as far as the name is concerned. So we'll skip down to number 4. So these mechanisms are known as Sn1. The 1 is for unimolecular, so substitution, nucleophilic, unimolecular. And so though this is unimolecular, this occurs via 2 steps. So be careful with Sn2 versus Sn1. Sn2, one-step mechanism involving both the halogenoalkane and the nucleophile in the rate determining step. Sn1 occurs via a 2-step mechanism where only the halogenoalkane is involved in the rate determining step. So let's take a look at the mechanism for this reaction. Let me draw out the reactants. So in the first step, we have this occur, where it's not the partial breaking of this bond, but this bond breaks completely. This is via heterolytic fission. And so what we end up with is this. Now this lost a pair of electrons, so what do we make? We make, of course, a carbocation. Now, what kind of carbocation is this? This is a tertiary carbocation, which, as we talked about in previous lesson, this is more stable, say, than a primary or secondary carbocation. All right, so now we have not just a region of positive charge, but we have a very powerful, strong positive charge on this carbon atom, which again makes it susceptible to attack from a nucleophile. So lone pair of electrons there, and that nucleophile forms a bond with carbon. Should be noted that this step is slow, the formation of the carbocation. So this is our rate determining step. Again, it only involves the halogenoalkane. Should also include here that we produce in this first step. So even though I'm kind of writing it all in one line like last time, this occurs via 2 steps. So here's step number 1, and here is step number 2. Notice that step number 1 is slow. That's a rate determining step. Step number 2 is fast, where we have the nucleophile attacking our carbocation, and we end up with our product here. So let's draw that out. And I already accounted for our inorganic product at the end of our first step there. So just like last time, let's recap what goes on here. So we have a tertiary halogenoalkane, which means that this is going to occur, this substitution reaction will occur via a 2-step mechanism where only the halogenoalkane is involved in the first or the rate determining step. So this bond breaks heterolytically. We produce Cl minus and we produce a carbocation. As seen here, this is a tertiary carbocation, very stable. This is then, this positive carbon atom is susceptible to attack from a nucleophile. So the nucleophile is attracted to that. So a lone pair of electrons on the nucleophile is used to make a covalent bond between that nucleophile and this carbon here. 2 steps, unimolecular in the rate determining step. All right, so here are some factors to consider when determining if the substitution reaction occurs via an Sn1 or Sn2 mechanism. Number 1, steric hindrance. Steric hindrance involves when you have bulky groups around a carbon atom. So large atoms, or you have, methyl groups. So it says too many bulky groups around a small carbon atom the result is that a tertiary halogenoalkanes favor reacting by Sn1 mechanisms. So meaning, if we go back to our mechanism here, Is there room for the nucleophile to get in here and form a covalent bond with carbon? No, you have these bulky methyl groups here that prevents, there's no way for the nucleophile to get in there and to form a bond with carbon. And so this does not occur via an Sn2 mechanism, but occurs via Sn1 mechanism. Also, another consideration is the positive inductive effect that occurs here. Carbocations must form in Sn1 reactions. These ions are more stable when the carbon forming the carbocation is surrounded by more alkyl groups. The result is that the primary halogenoalkanes favor reacting by Sn2 mechanisms. As mentioned before, tertiary carbocations are more stable than primary or secondary due to that positive inductive effect from the alkyl groups. All right, number 3, product solvents, which are polar, such as any solvent that has hydroxide, I shouldn't say hydroxide, a hydroxyl group like methanol or ethanol or even water, or an amino group. They favor Sn1 mechanisms. Product just means a substance that is able to donate a proton or a hydrogen ion. So any solvents that you have a hydrogen bonded to something highly electronegative, like nitrogen or oxygen or even fluorine. While aproduct solvents, which are nonpolar, such as ether or acetone, these favor Sn2 mechanisms. So depending on the solvents, you may get a different mechanism that occurs. Should be noted that we didn't talk about a mechanism for secondary halogenoalkanes. So primary halogenoalkanes will undergo substitution reactions via Sn2 mechanism. Tertiary halogenoalkanes will undergo substitution via Sn1 mechanism. And secondary halogenoalkanes actually undergo both mechanisms. So we'll deal with primarily either primary halogenoalkanes or tertiary halogenoalkanes. All right, that concludes this lesson on nucleophilic substitution reactions. Next time we'll talk about condensation reactions. Thanks for watching.